Good day, grade 10s. In this lesson, we're going to learn about EMF and potential difference. Now, it might seem weird to start our electric circuits with EMF and potential difference, but you guys know about the basics of electric circuits already from grade 9. Now we're learning about how the circuits actually work. So when a circuit is closed, charge can move through the circuit. In order to have this happen, there has to be a force that acts on the charges doing work. This force is provided by the battery. The battery has potential energy, actually a chemical potential energy, that's converted into electrical energy that allows the charge to move around the circuit. So the definition of potential difference is that it's the work done per unit charge. So what it really is a measure of how much work is required to get the little charge around the circuit. It's measured in volts. So the equation for this is V is W over Q, where V is your potential difference in volts, W is the work done in joules, and Q is the charge in coulombs. So it's all very well, but how do we measure it? So we use a voltmeter to measure our volts or our potential difference. The voltmeter is an instrument used for measuring the potential difference between 2 points. Now voltmeters have got very high resistance, so if we put them inside the circuit, they really mess with the circuit. You actually stop the current from flowing at all because they've got such high resistance. So what they do instead is they place them parallel. So we connect it in parallel and it's not part of the circuit. So now I'm going to attempt to draw a circuit for you. I say attempt because we know that I'm a terrible artist, but here we go. Here is a battery. 2 more cells make a battery. And we're going to put a little light bulb over there. And we're going to close the circuit. We're not going to worry about a switch. We're just going to close it straight away. Okay, now if I want to find out the potential difference across my battery, what I would do is I would place a voltmeter here across it. So do you see it's not part of the circuit? The conventional current of the circuit is actually traveling from the positive through here and back through here. So it's not actually part of the circuit. Or if I want to find out how much work is done per unit charge to get the charges through this little light bulb, I would put a voltmeter in parallel with that light bulb. And that would measure the voltage or potential difference across the light bulb. So you always put voltmeters in parallel with the circuit. Right. So now let us look at this little applet. Okay, so let us first of all grab a wire and then let's grab a battery. You'll notice that these are cells, but they call them batteries because if we're going to a shop and we wanted to go buy some pen-light batteries and we asked the shop assistant for some cells, they would think that we were mad. So we call them by the layman's term, which is a battery. Okay, there we go. Just make that nice and neat. Now we connect another, whoopsie, careful. It's very sticky. Okay. And then let's put a little switch in here. So that, and turn it, right. And let's join the wires. Right, so now do you see that we've got a beautiful circuit where we've got a switch, we've got 2 batteries or 2 cells, we're going to see the electron flow, and we've got a switch and a light bulb. Right, now we're going to get a voltmeter. And I also want to make sure, whoopsie, that I have, right, so let us move the voltmeter over here, so it's out the way, and there we go. And right, I just want to see something. Yeah, okay, there we go. Now if I close my, you see that the light bulb is, the electrons are flowing beautifully, and I close my circuit and I measure the volts across here. Do you see that there are 17.41 volts? Okay, so when the circuit is closed, we're getting 17.41 0.41 volts. However, if I open my switch, look what happens to the voltmeter reading. It goes up to 18. So when the switch is open and no current is flowing, the voltmeter reading across the battery is 18 volts. Just to prove to you that that's not just, look there, across the light bulb it is zeros. There's no actual potential is there, but over here it is 18. Okay, if I then close the switch, look what happens. Yes, it drops down to 17.42. So what is happening here? First of all, the one that we measure when we're across the battery and it is closed is called the EMF, whereas when we close the switch and we measure it, we're finding the potential difference. So when there's no current flowing in the circuit, the voltmeter measures the EMF. This is the maximum voltage that the cell or battery can supply the circuit, the maximum voltage. However, when the circuit is closed, the current flows and the voltmeter measures the terminal potential difference. That is the actual volts supplied to the circuit. So there's a big difference between what is actually supplied to the circuit and what the maximum voltage is that the cell can supply. EMF, maximum voltage, terminal potential difference, what actually is supplied to the circuit. The difference between the two is called the lost volts, and the lost volts are due to the internal resistance of the battery, because there's obviously some energy being converted inside the battery, and that's what's happening. So let's look at an example. A voltage of 6 volts is applied to a circuit to move 300 coulombs of charge. How much energy was required? So we've got V is equal to W over Q. We rearrange it, we get VQ equals W. So we've got the voltage at 6. Okay, we've got the charge in coulombs is 300. So our answer is 1800. So therefore, the amount of energy needed to move these charges is 1800 joules.